Lunch at Metalworks, December 10, 2016. And this uh, video, pretty much I want to uh, document what my thought, to capture some of it so I don't have to revisit all the time. Mostly for myself, but if you are watching this, and please bring a lot of patience, otherwise thanks for clicking and accident. It's about in terms of the edge, what performance, and when what you going to shape it, or what happened to it. And in my process, I just want to produce, say, like a blade with edge that able to withstand a bomb. But at time I got very kind of puzzled and confused, and then realized. What realization came is it's about the initial edge, and what happened to that. How thin it is, or the thick, or what's its strength, and then what happened from that point on determine a lot of it have to do from that point. It determines how your edge really perform. So if you for example, if you take, say, a straight razor, and if you cut into say a block of cheese or rubber, if you cut a little bit of it, it's fine. But if you push a little further and a little further, as long as you push perfectly, you can push fairly deep without damaging that straight razor. Because what I lead to is the steering, the deflection. That is the damage. That is the critical damage. When I look at it, say, if I would tack a piece of metal and ballistic projectile to it, you can see the metal usually get damaged by heat or impact, kinetic to thermal. But if you're talking about if it was your edge hitting a piece of nail, and you would think that okay, the impact damaged the edge, but then you can say the impact, but actually the steering did it in. Case in point like this. If you when the edge, well, there is the one that when the edge is softer than the nail, and then they got mush in. So that is the damage too. That's mush. That's the dent. It's not a roll, a dent. And then the other one is you just have chip. You see, the reason you see a chip is actually that means the edge is stronger than the nail, and it bent, it deflected, it bent, and you have the tensile of the bending on the longitude and the vertical, what that shape is. And when you exceed the viewpoint, where in this case elasticity viewpoint, and when you have hard steel, you might exceed even and into it doesn't have much plastic, then they just going to fracture. You have a chip. That's why you end up seeing the giant moon chips. And then for the but if you jump into the nail and you can see a part of your edge stuck into that nail, that is the bending, the I call steering from lengthwise along the edge and then verticalwise, and what that thing is, and they break off. And so therefore, if you were looking at optimize your edge, and if you say, okay, my edge start out from a certain point, and you say how many cuts I can make before I hit certain dullness, for example, or still workable. So the work done is like a curve. Initially, if you get really high sharpness, and usually you're subjected to damage instantly. It's not wear really, it's damage. If you have, say, you end up to say 400 nanometer, 200 nanometer, what you talk about is mainly damage, and you use very little and the damage, so very after a few cuts, not even, then you end up in the micron or few micron or even thicker very quickly. So those are the damage point. But if the work, the task, have deeper penetration and the deflection is further, but if the deflection or the steering is gentle, so or more like you bend something, the point. If you bend initially, when you initiate the bend, it deflected. And more like a four-wheel drive. You steer with only the front. The front now move slower. I mean less forward distance because it goes sideways. The back, the rest of the blade still go forward. So you end up with a skidding. But so therefore you actually accelerate the bending. So you go accelerate the bending. And well, you're going to, and then as you go into the thicker cross section of the blade, young model has about the thickness or the diameter of the test you want to bend. It allows to bend less because of the stretch and compress, and you're going to have damage. For highly ductile steel, then you have a ripple. In other words, you have a, and for the less ductile, then you have a chip. So today it will come down to is if you're optimizing it. Sometimes that if you, I think the key optimization would be the thickness, or in other words, the cross section of the apex, and then the radius of it, or it's as thin or as keen, but you can guarantee the damage is, I mean, you want to, the dulling effect is from wearing, from abrasive or whatnot, but wear rate, from wearing it, instead of damage, whether from rolling, or dent, or fracture. So, for people with really good sharpening skill, well, the tendency is you instantly produce really high sharpness edge. Then, well, the initial damage, it might be exceeding way past the point that where your working edge or the thinnest working edge possible. So you can have a you can accomplish a big workload during the optimal, like a bell curve, during the optimal point. But if your damage go outside of that, say a big chip, then therefore you no longer have to wither or slice or do things effectively. So you have to, what you have to do is make sure that you don't encounter that damage, that degrade you beyond the point of the bulk up of the sweet area that you can get work done. And so, I mean, I test a lot. And then from whether chopping or cutting everything, all these numbers around, we see some people say same blade fail on this, fail on that, and people have gut feeling or instinct or whatnot. It's just about sometimes that's it in your head, and you sorta depend on your skill level and your technique, and sometimes that save the outcome, but that's not really for me. I don't. For myself, I try to be say, qualitative in terms of what you try to do, and quantitative, it can be reproducible by, say, like a robotic thing, have no feeling to it. It's about physics, and you got this edge, or this and to do certain things. And I think I got, I kind of rambling along, but I lost some of my thought now. And I have a knife. This thing is thinner than a straight razor. A little parent knife, and I ripple it a few times. Yeah. It's pretty thin, and you learn. Even this thing, I can dull it to about 5 micron wide, and able to use. I can cut anything I need to cut. Mainly a lot of things. I mean, paring or even some cut into meat. Butcher, like a chicken, whole chicken. But the important thing is, if I press something deep with this thin, the steering kick in. So therefore, in order to prevent steering, of course, I pull toward me, and then they can move the point. But because it's thin, they can flex and curl around along with it, so it can do a lot of work done. But when I didn't make this thing, sharpen this knife into a straight razor level, and 500 or 500 nanometer wide, then a lot of damage happened right away, because the high edge thickness here, it would be like about 2,000 or 3,000 inch thick. So in all testing, I think if we, or I remind to myself later on watching this video, is it's about initial sharpness. You have to stop that steering. Once the steering happens, and you have to depth, it moves, and you keep pushing. And wow, this thin thing can bend more. But so be aware of that. Then you can look at that. You say, okay. Then you can compare. I mean, reasonably compare steel to steel, and say whether or not and also with certain initial sharpness, which one is better. And but also have to be apple to apple. And let's say if I compare, say, simple carbon steel, I mean low carbide volume versus high carbide volume, and the finish grade, even though you say I finished with the same stone, but the scratch pattern is different, because the more wear-resistant steel, the devil cut, the scratch is less. So, are you compare the same thing with the same initial sharpness, or actually you're not? The answer is you're not. Therefore, you have to do produce the same initial sharpness for both, even though geometry, everything the same. But the initial sharpness is the one that determines where you're on that curve of work done. Right? Let me draw from the camera perspective. If you imagine in the drop off way, and from the width there, you can go like this, and you can go like that, and that is this x-axis would be the thickness of the radius of the apex. So with that, I got distracted a little bit, sorry. So when many of comparison out there is, you have initial apex bias. And sometimes you say, you got sharper, don't mean it's better. You already put it in a disadvantage. So, I will remind myself, again, the same thing, the same concept there. I mean, I tested, I look at it. Again, bottom line for me is, can I whittle a dry bone with a 15-degree precise and finish with certain grit, like say in this case abrasive, and for certain carbide volume or carbide type as well, and see what relatively the finish of that apex, and the thickness and the keenness of it have to be equivalent. Anyway, so that's rambling on. It's all about that that initial sharpness and the steering. And go back to about the steering. When you chop, for example, well, a lot of time when we talk about the impact damage in it, I think I repeat this in a way. When you penetrate, initial, the edge is very hard. So a lot of time when you have to again chip, you don't see the whole blade crumble into like cookies. You don't. And so I just focus on the one when you have big chip right now. And so I penetrate, it steer, deflect it. And you keep pushing until the band can no longer the bend. Or more like you would go to bend the blade until it snaps. Except you bend this way. And when you got enough thickness, it's just going to fracture. If you have enough force still going at it. Even though in the beginning, it's very thin, it doesn't break right there, it's thin. It breaks way up here. When you say if you have baton cross-grain to a really solid piece of wood, or pine with the pin knot, all is about steering, and that will destroy it. That when the impact and lateral is not really lateral in that extent. It's you steer, and then the force begins to concentrate, and while the rest of the momentum of the blade still goes down, and that curve, that bend there, and you just buckle it, you just break. And the same thing for cutting. Well, at the extra thin level, you do the same thing. And then you say, oh, I just post-cut some crusty bread, and why my blade chip or roll or whatsoever. It's about the initial strength, not enough. And that little crumb there deflect your very apex a little bit. You press down, you destroy it. So in real life, and that's why sometimes it's a curse to sharpen, or you're too good at sharpening. You end up actually inflict poor performance for yourself. But when you're aware of what you're doing, or whether or not you're doing a one-sided micro bevel or all these things, you have, and then how sharp you want to do things, and whether or not the cut ended, say you're a kitchen knife, cut ended with an impact to a cutting board or air cut. All these things get you take into consideration. And well, hopefully I will take consideration when, after a while, I resume back and I will look at this video. And I got more thought, but right now that's all I can remember. Maybe I will make another video, or or yet augment to this one. And let's see, before I shut up, I have to think a little bit here. Well, I guess what really bring me is, I'm making a lot of these high carbide volume, and mainly a lot of vanadium steel. And at a point I can just cut things like a bandit, and no problem. At a point that time, and I see the initial early chip, and again, go back to that, is all go back, and then I look on the microscope. It's clearly to me that initial sharpness did a lot of the damage. But then when you lower the hardness, say when you lower a little bit, then you do reduce you still have fracture or bend or roll a little bit, and then it's fracture. But then you sacrifice it, and you get the edge to certain thickness instead of drastic damage until the steering keeps going. You actually help it, and the steering sooner. So I think there is the balance, yes. How much if you are too sharp, and when is the failure? But if you have something, super soft, you say, very ductile and ready, very weak, then it's foil over right away, and you pretty much fold up the apex, and you still press onto it. But when you have something already on the side, now just a matter of how much force, how much can you roll up. Think of like rolling up the edge. How much force can you roll up as far? That's why if you chop into a nail, then you can see the shape of a nail. Indentation, it pretty much is rolling up to that point. And you say, well, that better than a chip? No, it's, well, you still lost that much steel. But a chip, well, for the chip, but now for when you baton to the same way, the the fracture I do observe is anywhere could be from, you know, it can be drastic. It could, your blade could snap in half. Like say in baton, and you have massive force put down on it, and you shear it off. But and then you can snap the blade. Yeah, I mean, you have to say, oh, you know, the stress rises, this and that. No, you mainly about shear it off. And for the, you know, for the really sharp blade, and you have a ripple or bacon or all sort of things. And for, but it all come down to, oh yeah, I mean, this thing, it's about strength, and is able to resist. How strong this thing be. Now you deal with, okay, steering, fine. But now you say, how strong it is to resist it. So the stronger it is, the less it will bend. At some point, your force will go down, and it won't go down anymore. That's why sometimes if you are testing and you patonting and everything get bounced right off. I'm not talking about splitting wood. I'm talking about cut across. Splitting off. With the same thing, I still like edge geometry, but with a very rounded edge, and you chop and it bounce. It's so great on soft 2x4, but when you chop something like a knot in oak or something, and your chopper get bounced right back. Well, yeah, I mean, it's about, making that contact. At some point, your edge is no longer optimal, therefore, of course, performance drop. So, balancing that and willing to be able to sacrifice you can see the temptation of extra thin edge when you don't have to, if you are looking at the total amount of work can be done. And the good thing about high alloy steel is there's a lot of carbide on it. And if you structure it correctly along the edge, along the apex, and around right next to on the lips of it, there are a lot of a lot of carbide. And though I like your little micro saw teeth, you can saw it. And so you can use it as a working edge. You can, as long as you don't go for sub-micron edge, you can say you have 3, 4, 5 micron wide edge, and you have 2 micron to 3 micron diameter carbide as a teeth, a serration, think of that way. Then you have a long working edge. So I think if we, okay, just take away would be, got the edge in a way that you can, optimize it in a way that you can minimize the steering, strong enough to minimize the steering for the task to be done, so that you don't have major damage that take degrade the edge beyond the working, the one on when you begin wear mode, where the degradation is from wear instead of from damage, from mass damage. So a chip or a big roll, the big roll is almost increased. I mean, when you have like this, when I go like this, how thick is this thing? It's a lot thicker than, if I have a chip, I might, the width is actually thinner than a fold. So sometimes, but if you are, even that, I mean, you have to choose too. Sometimes the damage mode is, and if you do a lot of slice, a microchip is not a bad thing, because you can slice and shortcut. But unless you are draw to a nail or something and you have consistent, even that, the microchip not evenly. But if you have a soft steel and you draw on a nail, they all fold like this. Then now you have almost, you try to cut thing with a wire, a round wire, because you have a curvature. So it won't cut anymore. So all these things is about your trade-off and what is geometry and how thin that initial point. All right, well, done rambling for today.